This is 2.6. And the topic is continuity. Okay, so before we start, let me give you a quick overview of what we did before. So that was 2.4 and 2.5. 2.4 was limits, infinite limits. Let's look at an example. Let's take something like this. So limit with x approaching 3 from the right. This is plus. Okay, and then the function is 2 minus 5x. And then the bottom is x minus 3. Alright, so we're trying to figure out where the function is going. And we see that you cannot plug in that 3, right, into the function. So, and there's now algebraic tricks that we can use to simplify it so that we can plug it in. So what we'll do, we'll simply take that 3, and we can always substitute that 3 for x in the numerator. Okay, so let's do that. So if I do that, I will get 2 minus 15, so that's going to be negative 13, maybe negative 12. Okay, so we have a negative number, and if we plug in a number that's slightly bigger than 3, like 3.1, right, so we're going to get a number that's positive in the denominator. So that's a positive number, right? So positive, and these numbers, right, the closer I get to 3, right, the numbers will be getting smaller and smaller. Okay, so I'm dividing some number, well, negative 12 in this case, by smaller and smaller number, so I'll be approaching negative infinity. Okay, so that was limits. That was limits, infinite limits. The second thing we did was limits at infinity. So limit at infinity, or limits. So that was those problems where you have limit, where x approaches infinity, and then we were doing those algebraic tricks. Let's do maybe 3x squared plus 2x minus 4, and let's divide it by, say, 2x squared minus 7. Okay, so we were, I think maybe the most useful, the simplest way to solve it would be to factor that x squared out. Infinity, so we'll have x squared, then I'll have 3, plus, after I simplify it, I'm gonna get 2 over x minus 4 over x. Okay, and then the bottom is x squared again, from parentheses, 2 minus 7 over x squared. All right, so since x is approaching infinity, then something's missing here, square. Then this will go to 0. This approaches 0 as well. This approaches 0. So we get 3 over 2, right? And here these 2x squares cancel out. So the answer is 3 over 2. Right? So that's the limit. Okay, so that was the second thing. And the third thing we talked about asymptotes, right? So there's a definition of asymptote. where limit is approaching a vertical. I'm talking about vertical asymptotes. When limit is approaching a certain number, and so let's write the definition. So limit is with x approaching a certain number of f of x. Okay, so that equals either positive or negative infinity. So if that's the case, then x equals c. So then this equation is equation of a vertical asymptote. And then there's that catch, right? When let me give you an example. When you have a function, so f of x, let's say we factored it already, right? So we have x minus 2, x plus 2, and x minus 1. Okay, so that is the numerator, and the denominator is, let's say, x plus 1 times x minus 2. Okay, so you see that, right, we can cancel these two factors so that the function will have a whole at x equals 2. And when we cancel a factor, that gives us a whole and vertical asymptote at x equals negative 1. Right, so I got that whole from these two factors that I canceled, and asymptote from the factor that didn't cancel. Okay. All right. Yeah. So for today, the topic is continuity, and the function is continuous when I'll give you a formal definition later. For now, let's just say that you can trace the graph without lifting the pen off paper. Okay, so continuous function, this is S, so can be traced without lifting a pen, of paper. So graph, right? Paper. Yeah, so let's look at example 1. Yeah, so maybe before I give you that example 1, I'll show you a function that's perfectly continuous. Right, so it could be like a cubic polynomial, for example, right? So something like this. Right? And you guys saw that I drew it without lifting my pen off the paper. Yeah, so this is a continuous function. So let me show you an example of a function that is not continuous. So f of x equals 1 over x. Okay, so here's the graph. All right, so we have those two branches, right? The hyperbola, left branch, and the right branch. And yeah, obviously this function cannot be traced without lifting the pen of the paper or screen or whatever. And yeah, you can see, right, there are two separate branches, and yeah, the function is not even defined, right, at that 0, right? So obviously it cannot be continuous. Anyway, let's write it down. So not continuous. And at that x equals 0, and let's write a couple other comments that maybe won't make sense, but I hope soon they will. So let's write, so we have that, let's write, not so the function is not continuous. We have that at x equals 0. The function is not defined. At 0. Okay, that's the second comment. And let's write discontinuity. I don't know if that's how you spell it, but whatever, it's here, cannot be removed. It's a non-removable discontinuity. Cannot be removed. Okay. Yeah, so maybe in a moment I'll explain what that all means. Let's just add one more comment. So it's because as x is approaching 0 from the left, right? So I'm approaching 0 from the left. So where am I? Right, so we're here. We're going this way, 0 from the left. And if that is happening, then the y's are going towards negative infinity. So f of x, comma, f of x is approaching, right? So that limit is going towards negative infinity, or is negative infinity. And then when I approach 0 from the right, I get positive infinity. Okay. Okay, so yeah, let me show you a function that the function that is also discontinuous, discontinuous, but the discontinuity can be removed. So example 2, and it looks, this is our old familiar f of x equals x squared minus 4, and divided by x minus 2. Okay. Yeah, so that was that function that we can cancel those two factors. So x minus 2. Can I fit it here? Yeah. So x minus, if I factor the top, right, I get x minus 2, x plus 2. Divided by x minus 2. Alright, so we can factor, we can cancel these two factors, and we get that equals just x plus 2. Okay, so let's graph it. Okay, so what does it go to? This is 1, 2, this is 4, negative 2. Okay, so it's just like a regular y equals x, right? Just 45 degrees, right, line. And it's just shifted up by 2. Okay, so let me draw it. And I know it's gonna, so I know it's gonna have a hole, right? So I'm gonna put that hole right there. Let me make it blue. Right, so it has a hole at 2. Right, as I was telling you at the beginning of the class, right? When I cancel a factor, that factor gives you a hole. Okay. Yeah, so that's the graph of our function. And now, so let's write our conclusions. So the function is discontinuous. Again, forgive me the spelling. But that discontinuity is removable. So let's write removable discontinuity. Okay, let's add those numbers here. So this is 2 and this is 4. Okay, so basically that means that the function can be repaired, the discontinuity can be removed because the limit. Right, so you see that if I'm going towards that 2, right, from the right, my y values are approaching 4, or maybe this way, right? Doesn't matter. If I'm approaching that 2 from the left, right, my values of the function are also approaching 4. Okay, so in that case, we can actually remove the discontinuity, and we would do it by, redefining the function slightly. Yeah, it's going to be a different function, but it's just a slight difference. Okay, so we have the original, right? X squared minus 4 divided by x minus 2. And then there is this condition, right? So if x does not equal 2. Okay, let me make that line shorter on this one. Okay. All right, so yeah, so that's right, part of that function, and then we'll just write 4 if x equals 2. Okay, so we redefined that function, and we can do that only because let's do this. Let's take maybe not red. Let's do yellow, and then write because, and the limit from the left. So 2 with negative of our function is the same as limit from the right plus f of x. Okay. Yeah, let's do one more example. One more example where we actually draw something, right? Yeah, maybe 2 more examples, and then I'll give you the function. Okay, so example 3. I say 3 and then I write 2. Okay, so 3. So this one is defined like that, like this. So it's a piecewise function. So it's x plus 2 for x is less or equal than 0, and then x squared plus 2 for x is greater than 0. Okay, so for now we don't really know how to do it algebraically, right? How to check if the function is continuous. So let me maybe write a problem. So let's write let f of x equals this. Maybe discuss continuity. Okay. Yeah, so that's our task. We'll basically decide whether the function is continuous or not. Okay, so yeah, let's graph it. So we have a parabola. So this is, and that's the only method that we have, right? Just graphing it. So we have to be pretty careful when you're graphing it. So 2, 4, negative 2, negative 4, negative 2, negative 4. Okay, so first function we have is x plus 2 for x is less or equal than 0. So what I'll do, I'll take maybe different, right? So this is let me put those down, write those numbers. This is 2, 2, negative 2, 4, negative 2. Okay, let's make it blue, and I'm going to make it dashed. Right, so we already know how this looks, right? X plus 2, and I'm just going to sketch the graph of it. Okay, so something like this. And what we need is the part of the function. So it says, right, x plus 2 for x's, we're here, right? Should be. Let's make it blue. Right, so this is our function we're graphing currently. Okay. Okay. Oh, I got it now. So yeah, I want to keep the part of the function, right? So I'm looking at this part of the function for which x's are less or equal than 0. Okay, so I'm going to just erase the part of the function that I don't need. And I'll take that blue and I'll make that solid. And because I have solid, I have less or equal, right? So that equal is responsible for that closed hole. Okay, and then I keep this part, right? So that's the part I will keep. Okay. All right, and then we have the second function, right? That's the x squared, or second part of the function x squared plus 2. Right, so that's a parabola. And again, I'm going to just sketch a graph first, and then I'll think which part do I erase and which part I keep. This is not nice, but I can make it a little better, maybe. All right. So yeah, I look at this condition, right, this one here, and it says for x is bigger than 0. So I keep the part of the parabola that is to the right of the y-axis. Right, so this one. Okay, so this is our y equals x squared plus 2. And here, the blue one is y equals x plus 2. Okay, so yeah, what is the conclusion? The conclusion is the function is continuous. F is continuous. By the way, right, when I'm checking that continuity, I don't really need to check the whole function everywhere, right? I know that. Let me put the arrows here. This and that. Yeah, when I'm checking that function, I see that when I look at x plus 2, right? X plus 2, we know that the function is just a straight line, and that function is continuous, right? And then the same thing with that x squared plus 2. Right? The function is continuous everywhere. So the only point of discontinuity that may happen, that may exist, is that 0. Right? Because they may simply, right, not be connected. Right? If we take, for example, let's take let's look at another example, right? Just quickly. So example 4. So something very similar, right? So f of x, and then we have to do x plus 2 for x is less or equal than 0, x squared, but this time plus 1. Okay, x is bigger than 0. Okay, so quick graph. And I already know what's happening. I'm not going to sweat over it. Right, so the blue one, this one, and x's are less or equal than Right, so I'll be here. This is the graph. And now the yellow graph. And it's gonna be, well, this is 2 and this is 1. So now the yellow graph is here. So there's an open circle right there. And that's that parabola. So you guys see that now, right, the function is not continuous, discontinuous. So this continues. Nos t. So discontinuous and non-removable, right? Discontinuity is non-removable. Non-removable. Right, and I hope you kind of remember why, right? Because those limits, right, are different. I'll write it more precisely, better later. Okay, so if I'm approaching 0 from the left, the value of the function approaches 2. When I'm approaching 0 from the right, the value of the function is 1, or the limit. Okay, so those limits are not the same. Okay, so I have one more example. So example 5. So example 5. And again we have to discuss the discontinuity f of x. Again, it's a piecewise function. So the function is equal to 1. F of x is equal to 1 for x's where x's are different than 2, other than 2. And 3 if x is equal to 2. Okay, so again, graph, right? That's the only way we can figure it out. Okay, and then this is 1, 2, 3. Two, 3. -1, -2. Okay, so yeah, let's graph it. So this one will be green. So it's basically it's just a straight line, right? At 1, y equals 1. But then when I get to 2, there's an open hole, and that value actually at 2 is 3. So it's like this. This is my blue function. Okay, so obviously the function is not continuous. So discontinuous. There's a break, right? Yeah, and the question is, well, is it removable or not? Well, it's removable. That's a discontinuity is removable. Okay, so what is the definition of that continuity? So definition. So function f is continuous at some number c, at c, if, and we have 3 conditions. Okay, so the first one is the function must be defined at that point. So f of c is defined. Number 2, the limit exists. Limit with x approaching c exists. Okay, so yeah, I hope you understand the first, this part. The second part, right, I need to have limit approach when x is approaching that number from the left and from the right that limit needs to be a number. It needs to be at the same number, right? So that's what exist means. And yeah, the third condition. Okay, so limit with x approaching c of that function needs to be the same as the value of the function. Okay.